to introduce you to Dr. Kobus Barnard. He's standing right behind me, like I mentioned a moment ago. Tonight's talk is Theories, Models, and Data. And just to give you some background on our speaker, Kobus received his PhD in computer science from Simon Fraser University, a wonderful Canadian institution, in computational color constancy, which is a research area that helps your phone take better pictures. Very important. He then spent 2 years at UC Berkeley as a postdoctoral researcher, where he inaugurated the research activity auto-annotation, which is inferring appropriate caption words for images. His research interest, well, he's been at the U of A since 2002, and he's interested in computer vision, that is making computers see, machine learning, which is making them smarter, and scientific applications, which is making them help science. In particular, he's interested in integrating world knowledge and observed data into models that are both predictive and explanatory. And last but not least, when he's not developing statistical models for computers, he takes his chances doing some dangerous sports, including rock climbing, mountain biking, and skiing. According to him, he eventually plans to grow up one day. So tonight, Kobus will draw some connections between theories, models, and data, like the talk implies. He hopes that you'll learn what a predictive computational model is, what an explanatory one looks like, how modeling is related to theory building, and how big data and computation provide opportunities for doing these, but also present a lot of challenges. So let's put our hands together for Dr. Kobus Barnard.
Mic on? Yeah. Well, thanks for the great introduction, Barbara, and thanks for College of Science for these venues. I think this is a great thing that we do, and thanks for coming. So I just need to find the, oh, I need to get the projector talking to the computer. Yes. All right. Okay. So stand back, I'm a technology person. Okay, so as has been said, this is talk number 6 in the series about taking a bite, spelt, of course, with a pun, out of big data. And so when I was preparing this presentation, I'm thinking, well, am I an imposter? Because I actually don't really rely on big data that much in my research. And I was tempted to call my talk Big Computation, Big Data, Big Deal. But then I thought a little bit that I have done some work in big data when big data was small, and it is actually relevant to a lot of things I think about. So what is big data? Well, it's our emails that Google knows about. It's our images, our blogs, our videos, things we put on Facebook. It's in this talk series we've been coming regularly. You've heard about astronomy data. Genomes take up a lot of disk space too, and so on, and it just gets bigger and bigger. Okay, so there's a lot of reasons why that may or may not infatuate someone, but I'm asking, well, what's the big deal for me? And I think that there's two things that have been in part of my research for a long time, and it's just getting more important. It's getting more important to understand that data with machines, because it's growing bigger than our populations. They're not going to find humans to look at it and figure out what's going on. So to use it to a real advantage, we need smarter machines. And that's sort of something I've been working on for a long time. And then the data affords opportunity for discovering things that maybe we couldn't discover elsewise. Okay. In this series, I'm sure you've been convinced, if you've been coming, that big data is associated with big technology. And I'm going to talk a little bit about how that might work, but I'm not actually going to spend much time on it, because that's not mostly what I do. I'm really interested in to get an insight. Are there insights out there? And this will become clear what I'm trying to accomplish shortly. So here's a brief outline. I'm going to talk about classical machine learning, some limitations and pitfalls. I'm going to talk about computer vision with representation. So this isn't meant to be a political statement. This is just something that I've worked on a lot. So I chose to talk about it. And then theoretical development using computational modeling. Okay, so these are all in their own way part of an academic sense or categorization, machine learning. I'll talk about classical machine learning, probably what you think it is, because it's the most common way to think about it. But first, how many people have heard of machine learning? All right, many people. Well, that's good because it's going to rule your life shortly. It's already in charge of what ads you get to see. It'll soon be telling your self-driving car to turn left or right, and maybe it'll tell you what medication you should be on and everything else. So it's good that you know about it. So let's talk about classical machine learning. So the classical task is to take a pattern and develop a learning machine, or this box here, that outputs some, say, label, category. So this image here gets put into the category of tiger images that has the label tiger. And that's basically it. This is how it works. I mean, this could be a song, and this could be the person who wrote it. But it doesn't take very long to understand what this thing does. There's this data, and it produces a label because the person, we have maybe labels for some data, but not all of it, so we might want some. How do we do that? So, 3 steps. You get some training data. We're not going to solve this problem without examples of this and the associated label. So get some training data. We're going to build a classifier. That's the mathy part that maps example data into categories. There's all kinds of ways you can do this. The current buzzword is deep neural networks or convolutional neural networks for images. And then you have to check that it works. What happens if it works really well? Well, you contact the New York Times. So I'm only a little bit envious that this paradigm gets all the press, but anyway, I'll get over it. We need to make this work, we need lots, I'm going to go back, we need lots of these images labeled, for example, if I'm only talking about images. So where does that come from? Well, one way is clever use of existing data sets. Something I've worked on. All these people want to have other people see their images, so they tag them in the image sharing thing. Well, that looks like a fun thing to do with images, but to a machine learning person, that looks like data I can use for training. It used to be also we used undergraduates to label things. But now we have this thing called Amazon Mechanical Turk, and I'm actually very curious to ask how many people have heard of that. Not many. That's fine. I was astonished, though, that my class, graduate class in computer vision, no one heard about it either. So, okay, it's changing the world, so we better find out about it. So you can go find it pretty easy, and there's a logo that says who's in charge of it. I'm sure you've heard of Amazon, right? So you can go there and you could set up your own little experiment over here, but this over here, you can choose to make money by working on hits. What's a hit? It's a human intelligence task. And you can do things like label images of tigers with the word tiger for money. I kid you not. You can do this tonight. If you need a hobby, you can do this tonight. Now, it's not a lot of money, okay? It's not a lot of money. Let's be honest here. But it's a global thing, and there's this global project. There's almost 600,000 of those tasks that you can choose from. Of course, we got search and stuff. Okay, so you can help provide data to train these machines to help change the world. So you might, in one hit, you might see this image, and then you type this, you type that, and so on. Now we're ready to go. What do? Well, we take all that data from all these people all over the world typing in that stuff. We put it into to train this big thing here, which is a convolutional neural network, but it doesn't matter. And it's running on this compute cluster over here. And what happens is we come up with a black box. And the black box is now ready to see new images that are somewhat similar but different than the ones that it was trained on, such as this one. It's not the same tiger as before. And choose the label for it. Okay, so that is how we do that. So let's ask a different question. Let's do a different categorization. Let's ask something a little more serious. How long will you live within 20%? Okay, so I don't have a picture of you, so I put one of me here, and you say, well, given that picture, it's not long. But, you know, big data, you can train a classifier to do anything, so maybe we can pull this off. Of course, I don't care how old the photo is. What I want to know is me, so I'm just saying that was a stand-in for things like my genome. Like, think about wearing sensors on your bodies, little things that stick on for your whole life to keep track of everything that's going on in your body. Eventually, this could maybe be possible. I have no idea. Anyway, so the data goes in the black box, and we get the result. Once it's trained up from other people, we get the result from me, and it says 2 months. Wait a second. I know this is all very smart, but can I get a bit more? All right, so there's going to be a couple issues with this. You might want to know why the machine says what it says. You might want to know how to change the answer. You might want to say, should I quit climbing, reduce my drinking, or get meds? I don't know. But that, you know, I just don't want to know when. I want some control. So, well, no can do. This is where we say, what part of black box don't you understand? So the state of the art of classification, it works very well. Compared to even a few years ago, it works surprisingly well. Why? Better training paradigms, bigger computers, bigger data, and Amazon Turk, and other stand-ins. The bad, I don't know how it works. I mean, we know approximately how it works. It's not really that mysterious, but how it really works in a particular situation is really hard to figure out. And even though they're very accurate compared to what we did 15 years ago, they still can make very embarrassing mistakes. People have designed, say, okay, my paper is going to be about designing a picture that looks exactly like this tiger, change a few bits, and it'll get wrong. I kid you not, this happens. It's very specific. We trained up a thing about how long I was going to live. If we have to train up something about what's my best medication, we have to start from scratch. There's no overlap at all. So it's not suited for providing mechanism. Okay. So if you have the good and the bad, you have to have the ugly. So the ugly truth is that it looks like a smart machine, and in some ways it is, but the world isn't involved. It maps one kind of data to another thing, image data to a label. There's no, there's nothing to compel it to understand anything more than that task. And so how it does it, well, that's what you asked it to do. It doesn't really matter. Is it useful? Well, the fact that the tiger label is accurate may or may not be useful if in your mind that's what you're looking for. But this whole link to the world is in your brain. So that's my caricature of modern machine learning. So I haven't been working on that, so I can make fun. I did some of that kind of stuff a long time ago. So an alternative approach is to begin with a constraint that I want something that explicitly represents the things I'm interested in, and potentially also encodes mechanism. So if it's going to be something about health, maybe I can figure out a way to use what it has learned from me and others about what to do about my problems, whatever they are. So it has to represent the world and model how it works. And this is conceptually distinct from modeling the data. It is surprising how much in academia, for example, this is confusing people implicitly. I think that the picture of the data about the tiger is really encoding data about the world, or sort of represents the world. It's not. So we can model the data, or we can model the world and connect it to data. Those are two things that I'm going to be talking about, the former. All right, so the reason why I want to do this is that we can make use of what we know. If we're going to design the system in this way, then we can put in things that we already know that we don't have to learn by having these training machines. We can answer a broad range of questions. If you know how the car works, you can debug all kinds of problems. If you just have something that detects something, well, you have to train another machine to do something to find some other kind of problems. And I'll hopefully get to testing theories by saying, if this theory leads to this model, and this model doesn't do very well, that says something about the theory, perhaps. Okay, so we have a question. Does your brain work more like the first plan or the second plan? Does your brain represent the world and model how it works? Any intuitive thoughts? Okay, I'm gonna try to convince you that the answer is yes. And vision, I think, is the easiest way to talk about this, mostly because I've done it for a long time. So here's a picture of some piece of furniture. If you're like me, you say, okay, some sort of desk, a bit of an antique. And although there's lots of exceptions and embellishments, it's approximately designed on the right angle system that just happens to permeate everywhere. Most angles in this room are right angles, and this leg is perpendicular to the plane of the desk, except for a few degrees due to the glue falling apart and stuff like that. Okay, so that's what we see, I think. Maybe I do and you don't, and you can never be wrong about your own perception. So if we disagree, that's fine. But the thing is, this is a right angle object, but there are no right angles in this image. Oops. There are no right angles in this image. So there's an example of the data doesn't have right angles. Okay. So the world, your visual field is full of parallelograms, and yet you don't see parallelograms, you see rectangles, because that's, you know the mapping from rectangles through a camera, and your eye as a camera becomes a parallelogram. So if you see this, you often think this. Do you believe that? I have an image to try to convince you. So this is apparently a true picture of a building in New York designed by a wacky architect. It looks dangerous to drink beer on this balcony, because if you put the beer bottle on the floor, it's going to go into the traffic. So those balconies are actually safe. They're just parallelogram shaped. And the only interpretation you can think of is they must be slanting downwards to make sense of the image. Okay. Modeling the world versus data 2. In images, people can be any size. They can be tiny. They can be big. This is just a property of how imaging works, and your eye works this way as well. So now I'm going to ask, see this person up here, the small one? Suppose I cut him out and stuck him in the foreground to compare the size with the others. Visualize that for a moment. Okay. Is anybody surprised by the size? Okay, so your brain is already working on this problem. Finally, one more example. Little videos. I mean, maybe I'll talk about videos, maybe I won't. But here's this woman, the second person on the right there. Let's watch the video for a moment. Whoa, she got abducted by aliens. All right, so in videos, people disappear. In the world, they don't. So what this, I summarize this all by saying the model of the world can be simpler than models of images. We don't have maybe 10 billion images labeled about all this problem, but if we just think about it and look at these examples, we come to this conclusion. So I'm going to talk a little bit about then modeling indoor scenes. And this is going to sort of introduce to you a different way of doing machine learning. And if the first method was new to you, I guess you get to learn several ways of doing machine learning today. Because let's start with this picture. So I'm not going to necessarily personally vouch for the decor in this image. And if you actually wanted to know if what the chances are that you show someone this picture, they think the decor is good, you could train Amazon Turkers, or you could ask Amazon Turkers for opinions on a whole bunch of images, and we'll build a machine that will probably answer that question. That's the first plan. But I'm going to ask a different question. Suppose I'm a robot, and I'm not just a robot, but one that likes to play pranks. So it's going to say, where can I hide? And it says, can I go here and here, behind there and hide? Is there a path, and is that a hiding spot? So do you think you could solve that problem? It's a kind of a blurry image, but if it was crisp, you'd be able to say, there's a step here, but there's got to be space between here where I can go. So to solve this problem, we can try to figure out the 3D geometry from that image and say, this image is of the world is 3D geometry, and if I'm successful, I would like to be able to, for example, make a floor plan out of that thing. And then I'd be able to do a little bit of robot planning for looking for hiding spots. So this is a problem that I've worked on a fair bit a few years ago, quite recently, in fact. How do I go from this image to this kind of representation where I clearly have some idea of the room that's in red, the frames, things like windows and doors in green, and furniture objects in blue. And so this is our problem. From this image, go here. Now, I'm not just trying to paint that image. The image on the right just demonstrates that I have a representation for the 3D geometry of the scene. We might be moving into perhaps the only technical part, or one of the few tiny technical parts of this presentation. So we're going to, I'm not going to worry too much about the room to start. I'm going to start with a simple example, dartboard. Okay. So you sort of know how darts work. You throw darts at the center, towards the center. Unless you're really good, they usually end up somewhere else. And that's how we play darts. But now I want to think about playing darts, and then I want to think about a model for what happens when darts are played. And if it sounds way too simple to be interesting, well, I tried to think of a very simple example. All right, so there's a dart, and they're just going to kind of fire up and land. So this isn't so much darts, it's a model of dart throwing. And so it's a model that generates statistical samples randomly, but with some pattern, slightly more likely to go towards the center here than otherwise. But my model is about a way to generate samples that resemble the world, what happens when people play darts. So that's one dartboard. There, I won't go through the whole thing. There's a second and there's a third. So dartboard games can be different, but they sort of have this property of darts sort of headed towards the middle. So these are pros, these are amateurs, and these are inebriated college students. But I try to keep it simple so I can distinguish two kinds of questions you might want to ask. So the first is, if I had the parameters right, so I can get these, well, I guess I can't go back because the animation, uh-oh, this is not going to be good. Yeah, I think we just have to watch it again. So we can ask, that is our model with the right parameters, and in other words, how much variance there is around the center, is it a good one for a dartboard? And further, by varying those parameters, can I capture all dartboard games? Maybe I can, maybe I can't. But the issue here is it's a statistical model for the data. I can think of the data that I observe as samples from this model. Okay. So all we're going to do is cast the room understanding question in the same way. And I'll call it a generative modeling approach for indoor scenes, because in the first case, we generated samples that resembled the world of dartboard playing. Here, we're going to build a model that generates random samples of pictures of indoor scenes. So they're generated from a probability distribution that encodes everything we think we know about indoor scenes, but about the scenes, not about the data. And we're going to think about how that becomes the data. So if the model is good, it should be able to generate the data. So for example, the model should be able to generate approximations of all these indoor scenes, and to have some dignity, it shouldn't generate too many of these other pictures. So can a black box do this? So I don't have a really good answer to that question. I think that if with enough data, quite possibly, but we wouldn't get out of this what we would know, what we want to know, which is about the world. And I think you would need a lot of data, because not only do you have to understand all these various images, you also have to understand this one, if the bed was turned around a little bit, and so on. So interior decorating activities would have to be all compensated for, as well as new ways to have an interior space. Okay, so how do we generate this kind of data? Of course, it's not going to be exactly that kind of data. It's going to be approximations, and it's going to be ones that have focus on the edges, but that doesn't really matter. How do we do that? Okay, so this is abstract and yet sophisticated, so I hope it works. So we have to start with the space, and the space could be short and wide or tall and thin. So that means we have to generate the room box. Then that's a boring space, so we have to generate one or more pieces of furniture. Again, it's just a sampling process. It's now structured to understand indoor scenes, but it's a lot like throwing the darts. Or if you prefer, once this dart lands here, you choose a different dartboard based on where it lands, if you like. Anyway, we have to generate some, oops, that's too many clicks. We have to generate some bounding boxes for the furniture and the type of the furniture. And then once we have the type of the furniture, we have to generate some pieces. Why? Because all of those are going to contribute edges to our scene. And so we have a model after doing this, but how do we get a picture? Well, we need to have a camera, and we don't know where it is, so we have to, that has to play a role too. And then the picture gets taken to this model image. Everything is pure and platonic in this process, but that, of course, isn't how images are really captured. There's also a noisy process of extracting features. That's the last step. So that is a model that tells us how to go from the world to the data. And it gets judged to be a good model if it does that well. And it's designed that if it were to do it well, we'd have access to all kinds of stuff. We'd be able to say, okay, not only did I map this image well, I know that there's 3 chairs, 7 whatevers, and the chairs are a little bit high. All that stuff is encoded. So that brings me to the question of how do you go from an image to this representation? And that's called inference. And it's hard. And that's what my graduate students spend most of their time worrying about, writing lots of code. We know how to do it very well if we had infinitely fast computers, but we don't. So we have to be clever, and that's where all the work goes. But conceptually, it's not that complicated. The system that I described can imagine rooms, right? In the same way that the other system could imagine where darts go. So the system can imagine rooms, and I can check that against the image and ask, how am I doing? If I were to do it well, things match up, then that's probably the model of the room. And the only flaw in that is that it's inherently very computationally expensive, so we have to do some clever tricks, and here's a couple of them. So I'm not going to get into that. That's the basic idea. I have a way to check any hypothesis for what's in the world against my data going through this kind of model. Okay, so here's just a little visualization of hallucinating rooms and seeing how they do. So, okay, it's not as smart as you. Next year, we'll do better. So here's it just stops here, and this is a random room box, which is kind of in the right direction, but what's the problem with this room box? It's a little high. Why is it having trouble finding the bottom? The bed's in the way, exactly. So it's only going to do this better when it gets around to hypothesizing or hallucinating the bed, at which point this gets fixed immediately. And on we go, adjusting the dimensions of the bed, and so on. So it's both very dumb and also actually very smart to even do it this well. But that's, well, one PhD dissertation worth of smart. All right. I'm just going to do a little time check here. I think I have enough time to show you one more example very quickly. I only have one video for this, so this won't take long. So we do this in temporal scenes as well, when we want to know not just the structure of the environment, but who's doing what. Or in particular, we've been playing with who's looking at whom and what. And so here we have the same video we saw before, but now we're going to figure out where they're looking, and we're going to represent that by a cone. But of course, it's projected into an image, so it's just this these two lines. And if we track the people in 3D, and we figure out their gaze cones also in 3D, then we know what parts of the world everybody gets to see. And here's just, and I wonder if I can, let's do it again, see if I can stop. Nope. One day I'll learn to control this technology. Anyway, you'll see that it's color-coded so we can figure out who's in the field of view of whoever. Okay, so this is just applications similar to before. All right. So now I'm going to sort of switch gears. It's all the same process, but I'm going to think about it in a completely different domain. And this is about using this kind of modeling as a way to collaborate with scientists on their theories. So typically, people want to come and chat to a computer scientist because they think they have some computational problem, and sometimes they say, I've heard about machine learning, it's really good. But eventually we come to the truth of the matter is that they're having trouble expressing their theoretical ideas in a computational model that can be tested. And the paradigm I've been explaining with the vision examples is really, in my opinion, very well suited for that, because it both encodes how you think you're predicting images, and then, of course, because it's predicting them, it's testable. So now we can say, not just, so in the case of the room, we already knew all we needed to know. We know how cameras work. That's an undergraduate computer vision course. We know about occlusion. I think you learned that when you're about maybe 2, and so on. But now we can, I think, we're now in the domain that we're going to use different styles of models, maybe one with occlusion, one without, to see that are linked to different theoretical ideas, and how well those models perform is going to indicate a little bit about the theories. So my question to you, do you think domain scientists care about representation and mechanism? Or do they just want to predict whether the asteroid's going to hit next week? Yes, no. Okay. They tend not to be interested in the black box because they can't publish that in their venues. They want to know what their theory. And this is, so here's my little metaphor for mindful modeling and collaboration. We have the theory, and we have the computational model, and we have the data. And those are 3 separate things, and the collaboration is in this middle box. I can create models, but I have no clue what a good model is for something I know nothing about. I have to really talk to that person a lot. They really know what they're talking about, but making that to a mathematical model is, well, if they could do it, they wouldn't be talking to me. So this is what I say the division of labor is. Over here, you have the scientists with all their knowledge and all their experiments, and over here, we have the geek who can do this, and there's a collaboration in between. Okay, so I'm going to do this in the context of emotional processes and conversations, simply because that's something we've been working on, or as an example of something we've been working on a lot with some collaborators in social sciences, social psychology, and they have some very strong ideas about this might work, but they actually don't know if they're true, so it's perfect to try this out. And they have all this theoretical stuff, and it doesn't really look like a model. And here's some examples. Emotions are multifaceted and largely social. Okay, that's going to take a little bit of translating, I think, before it's equations. Underlying emotional states ebb and flow due to regulatory processes and emotional interaction patterns, say, between you and your spouse, potentially have health consequences. And they got all kinds of stuff like this. And what we're going to do is build models that sort of say, well, do we see evidence of this in a predictive sense with a model that speaks to the constructs in their own field? So this slide could go on and on and on, but I'm sort of almost at my depth of understanding with those 3 points. This is really the business of these people. It's not my business. My business is to say, if you think that's true, this is the mathematical model that corresponds to it. But to ground this discussion, I will outline one of the experiments that we've looked at. So this is an experiment with 36 heterosexual couples, and they have different joint weight status. which I'll refer to as the weight is referred to as the body mass index, the BMI. It's actually not a very good measurement, really, but this is what they use. And those folks are discussed in the lab, all wired up with cameras on them, some topics about how they help each other be healthy, and or something like that. And you might think that this mutes the discussions a lot, being wired up, videotapes and so on, but apparently it doesn't take people very long before they just go on with their conversation. Anyway, so we have stuff like blood, so heart rate and breathing rate and that kind of thing. And we have the reported emotional state at various points in the conversation. How was that arranged? Well, these people, and they really do put out for science, I'd say. After doing all that, they have to sit in separate rooms and watch a videotape of the conversation they just had and have a little dial saying how they were feeling. That's represented here. And here's some data. And it's very messy. An example research question, and there's so many of them, but this is the example. Does the health status, body weights, impact emotional dynamics? And the questions are in the domain of people who are judged to be put in a category, say, of both partners are healthy weight, one is unhealthy weight, the other is unhealthy, and both are unhealthy weight. Okay, so what do we need in a model? We need to think that we need to be able to represent ebb and flow of these emotional processes and their dynamics. Do I know that there's ebb and flow? I don't, but I know that if someone theorizes that it is, I need to model it. So, then we're going to link that dynamic behavior to the moderators. A moderator here is purported to be the BMI of the two folks involved, or health outcomes like stress. Okay, so that's got to be in the model. And then, okay, no matter what kind of dynamic they're having, they're not going to be doing it perfectly for however long they sit in the lab. They're going to change a little bit. It's going to drift. The dynamics are going to change a little bit. All right. So, how do we do that? There's so many choices. So one is to think of oscillations for ebb and flow, and we'll use oscillators from physics to do that. So there's the simplest one, a pendulum. Oops. This is just getting used to how we're thinking about the problem. We don't actually use this picture exactly. So there's a pendulum, so we all know how that works. And if we were to plot the displacement over time, it has this nice curve that some of you may be having post-traumatic stress syndrome from way back when in physics, but that's how it is. Excuse me. Now, part of the theory is that some people will, or some couples, some dyads will help modulate their emotions or their partner's emotions during this conversation, dampening things. And that would be a damped harmonic oscillator. And that's a little bit like having this pendulum do its thing in water. What's the opposite of that? Well, I can't draw, but it's going to be adding energy to the pendulum with this little propeller. And it just continues to get bigger and bigger until the string breaks or something. Okay, so that's the kind of things that seem to be elements for modeling the situation. It's an example of a modeling process. But we so far have not actually had two people involved, right? All right, but they could be doing this, these oscillations if they're connected by, say, a spring. This is all very metaphoric. But if you do this, now you find that the behavior is quite complicated because they are dragging each other around with this coupling coefficient of their emotional state. And then finally, what about the moderator problem? I won't do outcomes. What about the moderator problem? Well, the idea is that it may influence the dynamics through how coupled they are. And that is the basic idea. Excuse me, I think my throat had exactly that amount of time in it, and now it's starting to go. Okay, so how does this look? Well, here's an example where the fit is good, and I assure you this data is very noisy and the fit won't always be good. But this looks complicated to begin, but what's happening here is the dotted lines are the model. The jagged solid lines are the data, and the blue is for the man and the red is for the woman. Okay, so there's a conversation modeled. So how do we do that? Those are the ideas. How do we do the math, so to speak? Well, it's a lot like the room, except I won't go into it. I'll go into it in even less detail. And just put out the little sampling process that is associated with this. Basically, this is saying that there's something about all couples that tells you about how their body mass index is going to affect their dynamics. The dynamics are coded in the theta. I is indexing couples. So this says there's some shared behavior I can learn from you about how I might be. And this says that, well, my BMI and my partner's BMI, all this is going to influence or bias these interactions. So this is the same thing as an image that had all the boxes nice and neat, and then we go from that to data by saying there could be noise. Okay, so I don't want to belabor this. It's already fairly technical, and I've skipped most of the details. But for the three people who are mathematically inclined, it's interesting. This notation, of course, could be just circles and arrows meant to express some ideas. We've all done that all the time. But this actually is isomorphic to math. So this could be drawn or shown in a much simpler form as that. And if you're a PhD student in my lab, pretty soon you'll look at that and see that, and you won't be able to tell the difference. Okay, so this is so the main, this is the recap of the modeling. I'll do evaluation and then I'm done. So the model is expressed in terms of theoretical constructs. I'm not qualified to know if they're good ones, but someone who wants to ask questions about those values has a tool to do that. And it's like the previous situation, it specifies the probability of seeing particular stuff. And so that is how we evaluate it. And the box is clear. Okay, so how well that works is an indication of the what someone should think about theoretically. So that leaves us with how do you evaluate something like this? And The answer is, like other machine learning paradigms, including the one that I outlined at the beginning, we evaluate models with the predictive power. So what does that mean? Can I use my model to predict something, say the future, or predict something I've never seen before? And how we do this, we're mimicking the eventual use of the model. We have some data, we take some and we pretend we don't have it. So we call that held out. We put it in a special place, train the model on the stuff that we admit we saw, and then go check it on the held out data, see how it does on the stuff that wasn't used to develop the model, and see how we do. How do we do? Well, we know how we did because we didn't know that data, so we can peek. And that's how every machine learning method is evaluated. The ones that are not evaluated that way get rejected. Okay, so I talked about that. And the last point about this is that because these models are complicated, they can do a good job of fitting the data. They have lots of parameters you can tweak so you can fit the data. But the more you tweak those parameters, the more you might fail on the other data. So, and that's called overfitting. So I'm going to go quickly through the results of the model that I saw, and there's only one point. So you can ignore everything else. And I won't go slow enough for you to see anything else. Can you spot the overfitting? I mean, I'll tell you what it is, but okay. So here's we've stacked up some models here. And we got some really dumb ones, the average. We fit a line. We let everybody do their own thing and ignore anything we've learned about others, and so on. So watch these numbers as I go down the list. This is the fitting error. This is how well the model does on the stuff that I trained it on. And then this is how well it does on stuff that I pretended I didn't have. So there are some numbers. And the stuff that you don't have is always going to be worse. I mean, not always, but 95 times out of 100 for sure. Okay, so there's this one. And a line, fitting a line to data is smarter than just taking the average. So this number is sure to go down because it has more power to fit. Whoa, these ones are going up a bit. That's already not looking so good. However, this one's got lots of power, so it really drives down the fitting error. Look what's happening to the predictive error. All right, so there is overfitting. And then the ones that we were talking about, this one, and then looking at the BMI, and we can see that the BMI helps a bit. Still wondering if it helps enough to really be 100% sure. But that is a way that the hypothesis that BMI matters did get tested. All right. So to conclude that section, the theory hypothesis linked to models that have to pretty much be co-constructed by computational scientists and domain scientists. The predictions for those models support the theories or not support it, or tell people where to look next. And because we designed them to be mechanistic, they can be used to answer what-if questions. Like, what if you responded differently in conversations with your spouse? Would their stress level change? You can think of a pretty good app here, right? You can imagine you get a little stealth message when you're really annoying your other and driving up their blood pressure and stuff, which isn't what you intend to do. All right. So mindful models need to address many important issues that for theory and applications that are hard to see how black box classifiers are going to do the job. More data helps because we can develop and evaluate more complex models. If I want a more complicated model, I'm going to overfit for sure unless I got lots of data to keep me in check. And so, big data to big insight, check mark. It's a muted check mark because some of that data you really need isn't that cheap. But nonetheless, if it's there, we know how to use it. So those are my collaborators on these projects, and I shall stop there.
All right, there's already a hand in the air. For those of you who might be joining us for the first time, we're going to do a little Q&A. On the far side of the auditorium is CJ, if you can wave to everybody there. And if you have a question, go ahead and raise your hand and we will make our way up to you.
Around 15 years ago, they decided machine language or machine learning would perhaps replace doctors, imaging specialists. They would just look at a chest x-ray and like the tiger, look for the cancer. Well, that didn't work out terribly well, and then they got a little bit more sophisticated and said we'll look at many more parameters and get more data. And it's just as your chart, the more they cranked up the sensitivity or number of abnormalities that they would find, the fewer of them were actually cancers that they were looking for. And the original prediction that you'd just be a Star Wars type scanner where not only would tell you whether or not there's a specific disease and tell you everything that was or wasn't there. And it seems like at Banner Health down at the university, they have millions of images with millions of data points for laboratory, age, gender, race, everything. That is this anything related to what I've heard you saying here? And is there, if there is, are you attached to that type of research or investigation at all? And the very last thing, why can't my power scribe on my computer at home tell the difference between TO, TOO, and TWO?
Okay, I don't know if I can remember 3 questions. So the data you describe is of interest, I think, to myself and many others. But it's going to be a while. So when I was a PhD student, my advisor told me that the history of AI, or I think he might have said computer vision, but computer vision is part of AI, history is simple to describe, it's failure. So it's really hard to have a good sense as to when those kinds of problems are going to be solved by machines. And as you've pointed out, the horizon is always 15 years out, which is maintained to be 15 years out. But the connection here is that I think that we need to understand a lot more about diseases and how they link to evidence about them mathematically before we're going to make that's going to be necessary to make substantive progress. It seems hard, and I've been hit with these problems myself. A collaborator comes to my office and we chat, where, okay, look at these, here's some images. I got lots of them, don't worry. If you need more, I'll take more of this slice, this biopsy, and that one, and they're all, you can have labels, and it's just really hard to build a classifier for that that's reliable. There's so much context that biases how those should be interpreted. So it's not out of reach, but the black box classifier approach is limited. So it speaks very well to what I was trying to say, is the short answer. You had a second question? Oh, the voice recognition thing. Yeah. Yes, fair enough. That's the sophisticated classifier failing when you thought that it had an easy problem. And why is that? We don't know. That's the problem. I agree. Okay, there's a second question, or yeah.
Are you familiar with IBM Watson and how it fits into this? Are they on the right track with that?
Well, I don't want to declare right or wrong tracks. They're on the wrong track, I think, for deep understanding. They're on the right track for the big technology. Is that the system that
That won Jeopardy?
yeah. Okay. So that may be a hard task for me, but I don't think it's that hard a task for a machine. But I was wondering, is that I mix all these systems up, but that might have been the system that also was asked where babies come from. And the answer was there's 3 baby stores within 5 miles of where you are.
I realize yours is visually based, but is something like this useful for translating languages? In other words, how would you translate language with a machine learning thing? You'd have to learn a language, I'm saying.
So yeah, that's translating from one language to another is there's a classic machine learning problem, and there has been progress, and we do okay, and it's the last 10% that's really hard. So is it related? I think it's related because the last 10% of mistakes is typically they're the hard cases, the cases where you really have to understand a lot about the world and how the 2 different languages work, rather than matching patterns of how 27 people have this sort of thing to that sort of thing in those 2 languages. Now, Amazon Turk, one of the popular things is translate this phrase into some language that some company has an interest in building better translators. So they've gotten better with bigger data, but the really hard cases where you have to understand metaphor, and you have to translate a metaphor from one language to another. I don't know if Amazon Turkers understand metaphor, but so it's related. That's not my area, but as you said, but yes, the issues are there. Similar issues are there.
When you were discussing the relating the images to trying to put it into a computer, program, I was thinking of the cars that are driving around without a driver now, and how they're seeing images and reacting to them. I mean, that's got to be pretty sophisticated, I would think.
Yes, I think that well, there's so much competition in the self-driving car situation, so many companies, and they're all secret. But I'm a fan of self-driving cars simply because it's providing employment for my students. I've got all kinds of students employed in that activity. So I think the going strategy is, so to begin, those problems are largely currently solved, as far as I know, to the extent they are solved, by mixed techniques. So the map is very important for self-driving cars. So one of the places where they're being contemplated to actually be allowed to work at a very slow speed are places where the maps are accurate, all the features are sorted out. There is not just vision, but there's also a range finding and so on. So having said that, there has been a fatality, and not a self-driving car, but a person who treated their car like one because it had very sophisticated self-driving safety features. And that it was debugged as not understanding that you can see through the bottom of a high truck. I think that's how that worked. So I'm not quite sure where I was going with that. A lot of visual sophistication, it's not clear how much you need for self-driving cars, but a lot of the understanding issues are still there. And but self-driving cars has a very interesting low bar. I think it's a low bar or high bar. Anyway, the bar for having your self-driving cars is to have less accidents than humans do. And that's not necessarily going to be so hard. But to really have 0 accidents, that's going to be a while.
I'm just trying to understand what you said tonight. So what I'm thinking is that the modeling inside the computer itself is critical to get an outcome that's true. And for example, in the BMI example, if people are interacting and BMI has nothing to do with it, but we've said that that's what we want to test, we might get a result that says that BMI, in fact, does have some effect. Am I making any sense? Because what I'm trying to say, if the model's not correct, the result, you can have all kinds of facts, but we can design the model to produce the result that we want.
Well, the model isn't designed to produce that result. It's designed to ask the question. But it is true that none of this gets you out of using your brain. It'd be nice if that were true, I suppose, but there's still scientific judgment on whether this is a reasonable question to ask. And there's scientific judgment on whether you accept the answer. So it's a tool to say, how can this, with this theory, this theoretical idea, this hypothesis of mine manifest in a model that I can test computationally? That's what's done. But there's still a lot of scientific judgment about what questions you ask and whether you believe the answers. Many questions, especially if it's a medical question, would have to be validated with additional experiments. And this is just making that process cheaper by reducing the number of real experiments you need. It doesn't get you out of the hard work of doing a real experiment to truly validate the answer.
All right, and I think I saw one more hand here in the center. Aha, never mind. Well, we have time for one more question. Any takers? Oh, okay, Carol.
Okay, well, that's a good question. So 97% at least of the code that has been written in the last 5 years has been written not by me, but my students. Most of it's in C++ and C. And the C also calls Fortran, just in case. I understand that's a hot topic, but yeah. And we prototype in MATLAB, sometimes.
And I'm going to ask one question. So what brought you specifically into computer science?
Oh, that's a tough question. So it wasn't a very straight and narrow path, that's for sure. So when I was young, I knew I was going to be a physicist, like my dad. And it wasn't a good time to be doing that when I was in university. And I was starting to have doubts that I was an academic. And so I did other things, and somehow it just became the right blend of activities to avoid growing up, which is the same reason why I'm an academic, I think. I toyed with the idea of getting a real job, but it just doesn't suit me. So, and I should say that eventually I came to the realization that my dad actually wasn't a physicist. He was a computational physicist before the word is invented. You know, he used like cards to feed into computers to talk to them. So I guess that sort of says it was in my blood, but it took me a decade to realize it.
Well, let's give Dr. Barnard one more round of applause.
Thanks.
As always, if you have any further questions, he'll be available up here on stage. And if you have any evaluations, feel free to hand them to either me or CJ, and we will see you back on April 6th at 6:30 for Dr. John Hartman and Data-Driven Science in the Cloud, which is the end lecture for the Taking a Bite Out of Big Data series. And thank you for coming tonight. Have a great night.